The universe is a big place, really big. It's so vast that it's almost beyond our comprehension. It's filled with billions of galaxies, each with billions of stars. These stars are scattered across the cosmos, creating a tapestry of light and wonder. Many of these stars likely have planets orbiting them. These planets come in all shapes and sizes, some rocky, some gaseous. Some planets might be similar to Earth, with conditions that could potentially support life. Imagine a world with oceans, mountains, and perhaps even familiar weather patterns. So, with so many planets out there, you might think there would be other forms of life. Life that could range from simple microorganisms to complex, intelligent beings, maybe even intelligent life more advanced than us. Civilizations that have mastered technologies we can only dream of. This begs the question, where is everyone? If the universe is so vast and full of potential, why haven't we encountered any signs of other life forms? This question is at the heart of the Fermi Paradox. Named after the physicist Enrico Fermi, it challenges our understanding of the cosmos. It's a puzzle that has baffled scientists and philosophers for decades. They have proposed numerous theories, from the idea that intelligent life is extremely rare to the possibility that advanced civilizations are deliberately avoiding us. If the universe is teeming with life, why haven't we seen any evidence of it yet? Are we looking in the wrong places, or are we simply not advanced enough to detect them? The Fermi Paradox is a call to explore the universe and our place in it. It encourages us to push the boundaries of our knowledge and technology. It's a reminder that we have so much more to learn. The universe is a vast, mysterious place, and our journey to understand it has only just begun. To understand the Fermi Paradox, we need to grasp the sheer scale of the universe. The universe is not just vast, it is almost incomprehensibly immense. When we look up at the night sky, we see only a tiny fraction of what is out there. Our galaxy, the Milky Way, contains hundreds of billions of stars. Each of these stars could potentially host planets, some of which might be capable of supporting life, and it's just one of billions of galaxies in the observable universe. Each galaxy, like the Milky Way, is a vast collection of stars, planets, and other celestial objects. Let's imagine shrinking our Sun, a star with a diameter of 1.4 million kilometers, down to the size of a grain of sand. This helps us put into perspective the relative sizes and distances in space. On this scale, the Milky Way would be as big as the continental United States. This analogy helps us understand just how vast our galaxy is, even when reduced to a more comprehensible size. Even at this reduced size, the nearest star to our Sun, Proxima Centauri, would be about 4 kilometers away. This distance underscores the vast emptiness of space between stars. Now consider that the Milky Way is just one of billions of galaxies scattered throughout the universe. Each of these galaxies contains its own stars, planets, and potentially life forms. Some scientists estimate that there are more stars in the universe than grains of sand on all the beaches on Earth. This comparison helps us grasp the sheer number of stars and the potential for countless planets orbiting them. The universe is a vast, mysterious expanse, filled with wonders we are only beginning to understand. In 1961, astronomer Frank Drake developed an equation to estimate the number of detectable civilizations in our galaxy. This groundbreaking formula was a pioneering effort to quantify the potential for extraterrestrial life. This equation, now known as the Drake equation, takes into account several critical factors that influence the development of intelligent life and its detectability. One of the key factors is the rate of star formation in our galaxy, which determines how many new stars are born each year. Another important factor is the fraction of those stars that have planetary systems, as planets are essential for the development of life. Within these planetary systems, the number of planets that are located in the habitable zone, where conditions might be right for life, is also considered. The equation also looks at the fraction of these habitable planets where life actually emerges, starting from simple microbial life forms. It then considers the fraction of life-bearing planets where intelligent life evolves, capable of complex thought and communication. Furthermore, It examines the fraction of intelligent civilizations that develop technology advanced enough to release detectable signs of their existence, such as radio signals. Finally, the equation takes into account the length of time for which such civilizations release detectable signals into space, which affects our chances of detecting them. The Drake equation is not meant to provide a definitive answer to the question of whether we are alone in the universe. Instead, it's a valuable tool for scientists to think about and discuss the various factors that influence the likelihood of finding extraterrestrial intelligence. It encourages collaboration and further research in the quest to understand our place in the cosmos. Given the vastness of the universe and the potential for life on other planets, it seems like we should have encountered alien civilizations by now, yet we haven't. This is the crux of the Fermi Paradox. There are many possible explanations for this paradox. Perhaps we are alone in the universe after all. Maybe intelligent life is incredibly rare, and the conditions that led to our existence are a cosmic fluke. Or it's possible that alien civilizations exist, but they haven't contacted us yet. They might be too far away, or they might not be interested in communicating with us. It's also possible that they are trying to contact us, but we haven't recognized their signals yet. Section 5. The Rare Earth Hypothesis. One possible explanation for the Fermi Paradox is the Rare Earth Hypothesis. This hypothesis suggests that the conditions that allowed complex life to evolve on Earth are exceptionally rare. Earth is in the habitable zone of our solar system, where temperatures are just right for liquid water to exist. It also has a protective magnetic field that shields us from harmful radiation from the sun. And our moon plays a crucial role in stabilizing Earth's rotation and climate. The Rare Earth hypothesis argues that the combination of these factors is incredibly unlikely to occur on other planets. If this is true, then we might be one of the only, or even the only planet in the galaxy with complex life. Section 6. The Great Filter. Another possible explanation for the Fermi Paradox is the existence of a great filter. This filter represents a barrier that prevents civilizations from reaching a certain level of technological advancement or from surviving long enough to make contact with other civilizations. This barrier could be anything from a natural disaster, like a massive asteroid impact, to a self-inflicted catastrophe, such as nuclear war or climate change. Or it could be something entirely beyond our comprehension. The Great Filter theory suggests that most, if not all, civilizations are eventually wiped out by this filter. If this is true, it raises a sobering question. Are we destined to face the same fate? Section 7. Hidden in plain sight. Some people believe that aliens are already here on Earth. They point to unexplained phenomena like UFO sightings as evidence of extraterrestrial visitation. However, there's no scientific evidence to support these claims. It's possible that alien life could exist on Earth in forms we haven't discovered yet. Or perhaps they visited in the distant past, long before humans evolved. While these possibilities are intriguing, they remain purely speculative. Section 8. A galactic zoo. Another intriguing hypothesis is the zoo hypothesis. This idea suggests that advanced alien civilizations are aware of our existence, but choose to observe us from a distance like animals in a zoo. Proponents of this hypothesis argue that aliens might be waiting for us to reach a certain level of technological or ethical maturity before making contact. Or perhaps they are simply studying us for their own purposes, much like scientists study animals in the wild. Section 9. The challenge of interstellar travel. Even if intelligent life is abundant in the universe, the vast distances between stars pose a significant challenge for interstellar travel. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. This means that even traveling at the speed of light, it would take over 4 years to reach it. Current spacecraft technology is nowhere near fast enough for interstellar travel within a human lifetime. Developing faster-than-light travel or other exotic propulsion systems remains firmly in the realm of science fiction. Section 10. A universe of possibilities. The Fermi Paradox is a reminder of the vastness of our universe and the mysteries it holds. While we haven't found definitive answers to the question of why we haven't encountered alien life, the search itself has led to groundbreaking discoveries and fueled our imagination. As we continue to explore the cosmos and develop new technologies, we may one day find the answers we seek. Until then, the Fermi Paradox remains a powerful reminder of our place in the universe and the endless possibilities that lie beyond our planet. What do you think is out there?